Hello, welcome back. So we're looking still at the idea of kinetic energy and going to do another little problem for you and just sort of get you the idea of what we can do with kinetic energy. So let's say that we've got the Earth. Go ahead and try to draw some North America stuff here. Here's some Central America. Here's some South America. Anyways, let's make Pluto pink. Let's say that Pluto decides to go off course, get rogue, and smash into the Earth. Well, what are some things we want to know about Pluto in order to figure out the actual kinetic energy of the impact of Pluto smashing into us? Well, here's a couple of things. We know the mass of Pluto. That's something that we've been able to calculate. So it's 1.30 times 10 to the 23rd kilograms, right? We know that, and you can look this data up, we know that Pluto has an average speed of 2 kilometers per second. Okay? Oops. So 4.72 kilometers per second. And so let's see if we can figure out something about the impact that's going to hit the Earth here. Well, first of all, let's go ahead and change this 4.72 kilometers per second into meters per second. So we want to go 1,000 meters is 1 kilometer and run that conversion unit so we have 4,720 meters per second. So that Pluto, it's going fast. It's going really, really fast. All right, so what else can we figure out? Well, now that we know the velocity, we can figure out the kinetic energy, right? So the kinetic energy is going to equal the mass, which is 1.30 times 10 to the 22nd kilograms, right? Times 4,720 meters per second squared, okay? And that's all going to be divided by 2. So the kinetic energy that Pluto is going to have when it smashes into us is going to be 1.45 times 10 to the 23rd joules. Now that is a lot of energy. Just to sort of get an idea of how much energy that is, one of our nuclear bombs, actually our biggest nuclear bomb, releases 4.2 times 10 to the 15th joules of energy. So if I divide that into that, I can actually figure out how many bombs that would be. And that turns out to be 34,478,476 bombs of energy, nuclear bombs of energy. So, needless to say, we would not like it if Pluto smashed into the Earth, and it would pretty much probably spell mass devastation on a global scale. So anyways, just kind of giving you an idea of some of the things you can do with kinetic energy. And so that was a pretty simple one. Let's go ahead and think of something that's a little bit more complicated. Let's say that you throw a baseball. Here's our baseball right here. And let's see. We got to give you a hand. Okay, there's your hand on the baseball. And here's your arm. And it should be connected to a shoulder. Maybe this is a bicep or something. So there you are. Here's a head, some eyes, a little hair. Man, my 5-year-old daughter could do this better than me. Okay, this is disgraceful. Anyways, let's say that you go ahead and you throw that baseball up in the air. All right? Let's say that you are able to put a net force. So you're able to put a net force on that baseball of 410 newtons. Okay? Let's say that the baseball's weight is 32 newtons. Let's say it's a waterlogged baseball that weighs 32 newtons. Let's say that, that's good enough. All right. So with that information right there, let's say that you are throwing that baseball for 2 meters. So let's say that you move your arm up, so you have a distance of 2 meters with this force of 410 that you throw the baseball up in the air. Well, here's what's going to happen. This is going to become kinetic energy, right? And that kinetic energy is going to go up, right, to a certain height, and it's going to transfer all into potential energy, and then it's going to come back down. So in this particular scenario, the kinetic energy is going to equal the final potential energy. So let's go ahead and try and figure out what we know. Well, we know that work, which is kinetic energy, equals force times distance, and we were given a distance and we were given a force. So if we take our 2, which is our distance, we multiply it by our 410, which is our force, right? We're going to have our work is equal to 820 joules. All right? And so then that's actually going to equal the kinetic energy as well, right? Because work equals the change in kinetic energy, and we went from 0 to 820. So that means that the potential energy also equals 820 joules, right? Because that's going to be the total potential energy when all of that kinetic energy is transferred and that baseball stops. So can we find the, let's say, can we find the height? What's gonna be the height that this baseball flies up to? All right. Well, here we go. So the potential energy is 820 joules. And what does potential energy equal? Well, you're going to have your mass, right, times gravity times 9.8 times your height. So that's what potential energy. Anything that is up in the air, anything that is suspended up in the air or has height to fall, has potential energy because of gravity. So this is called gravitational potential energy. That's the kind of potential energy we transferred into. We could also have elastic potential energy and things like that. But that's what this is. So mass times g times h. Well, the cool thing is we were given a weight here, which we already know is our mass times gravity, 32 newtons. So we can just plug that in. Equals 32 newtons times some kind of height. All right, so just divide 820 by 32, and the total height that our baseball is going to go up to is 25.6 meters. So this kind of problem kind of shows you how you can take the idea of kinetic energy and transfer it into potential energy. And potential energy, at least gravitational potential energy, equals the mass times the gravitational constant, which is 9.8, times the height. Right? So any of these problems you have where something is going straight up in the air, you could use this as the potential energy would transfer into that. So lots of different things you can do with this, and lots of different cool ways you can look at analyzing energy and work and seeing how they flow in and out of each other.